Hey, Algebra 2, I just wanted to finish up some of these notes from today and also clear up some confusion on the greatest integer function, which we had started off on this slide and then got a little bit confused on the next one. So let me explain it a little further and clear up some confusion. So what we had talked about, the greatest integer function, is simply a function with this notation right here, and it is also called the floor function, and it does round down. It takes every number that's inside that function and it rounds it down. It is not a truncating function, which I think I mentioned in class. It doesn't truncate the function, which caused confusion when we were going to negatives. So let me explain it a little bit more clearly, just to make sure if this was confusing, which I know it was during class, that we have it. So the greatest integer function, the notation is like this. It's kind of square brackets. And it has these little sidebars on it, but for the sake of simplicity, I'm going to just write brackets around it. So what this means, if I put a number in there, let's just say, 1.8, this will always round down, no matter where it is, right? So the greatest integer function is taking the greatest integer that is less than 1.8. This would give me 1. So when you do these problems, you can think of just think of the number line, and you're simply just going to the left here. So let's just put this on here, 0, 1, 2, -1, -2. So if I were to tell you the greatest integer function of 1.8, which is right here, you're always just going to go back to the left and round down to 1, no matter what it is. So if I have 0.2, right, 0.2 would be like right here. The greatest integer that is less than 0.2 is going to be 0, so that would just give us 0. And then when we go negative, so let's say -1.1 right here. -1.1 is right here, and we do not truncate that, which is a function, but it is not the greatest integer function. So we don't round up or truncate. We always round down. So in this case, it does go to -2. So just think of the number line, and no matter what value we put in that function, it just keeps going and rounds it down or to the left on the number line. Okay. So with that said, let's look at that example that we got a little bit confused on. So back to this function, we can really start plugging in numbers. Okay, and we're given the table of values here to actually go from, but if you weren't given this table, you would have to just test your own x values here and try to find endpoints or try to test integers, because those are going to be the endpoints. So in this case, for this first one, we could test -4, right? So if x is actually equal to -4, all right, I'm going to write this out again. So f of -4. And what that would mean is I'm going to take a half of -4, so 0.5 times -4, and then I'm going to say plus 3. And so I take, this is going to give me -2 right here, plus 3. And the greatest integer that is less than -2 is itself. It's -2. If you round that down, it's just going to stay at -2 plus 3. And that equals 1, right? So this right here is going to be 1 for my output. In other words, if I go to -4 on my x-axis and then I go to 1, I'm going to have this point that exists, right? So also we're assuming that any value in this interval is going to be the same. So if I chose x equals -3.5, which would also be in this interval, right? So what if I took f of -3.5 and I plug that in? Well, then I would have 0.5 times -3.5, greatest integer, or the if we round down there, and then plus 3. So a half of 3.5 is going to give me 1.75. 0.75. And then again, this is rounding down, not truncating. So this is going to round back down to -2 plus 3. And I get the same thing. I still get this 1, right? What happens if I plug in then -3? Right? So if I plug in -3 into this function, and we keep on doing this, so f of -3, and I say, all right, 0.5 times my input of -3, then and then plus 3. So this is going to give me -1.5 plus 3, and again, this means we're going to round down, not truncate. So this again goes to -2 plus 3, which is 1. And so this also gives us 1. And I think in class made the assumption that that always jumps up, and it's a step function that goes up, but it does stay at 1. Right? So basically I want to test all of the integer values that are going into this greater integer function, because those are going to be the boundaries of all my little steps here. So f of -3. So when I plug in -3, I also get 1. That means that -3 also goes to 1. All right, so when does this change? So we keep on going. I'll make some more room here. And when we get to -2, delete this. So we keep on going and we say, well, what about -2? What if we plug in that integer? We think about what is a half of -2, and then we're going to get -1, and then this thing is going to switch. So now what if we plug in f of -2, and then we do this function, which would be 0.5 times -2, or a half of -2. And then we're going to have plus 3. So a half of -2, this is going to be -1. And then we have to evaluate and say, well, what happens if we round down from -1? Oh, that's, again, going to stay as -1 plus 3. And so this is going to output a 2 now. So at -2, right, when I plug in -2, that function f of x will give me +2. So -2 up to +2, that's going to give that right here. This is also going to be the boundary of the lower, the step below it. So right here is going to be a boundary, and this whole line segment, okay, from -4 all the way to -2 in this case, is going to give an output of +1 right here. It's not going to go up to the next one. And so we can keep doing the exact same thing. The key on these functions is to kind of test the actual integer value. So then I would, check -1 here, or just think about it. So if I have f of -1, if I plug that in, a half of -1 is going to be -0.5 plus 3. Well, if I round this down, that's going to go to -1. That's going to go to the left on the number line, give me -1, and then I'm going to have plus 3, which is also going to give me 2. So this follows suit again. If I plug in -1, I'm still getting an output of 2. So that's right here. And then I can keep, so I'm making the assumption that if I plug in any points in between here, I'm going to get the same thing, right? Because if I take a half of any of these numbers in between, I'm going to have that round down function, which is always going to give me -1, -1, -1. And then I'm going to add 3, which will give me 2. All right, so then I go to the next end point here, and I go 0. Okay, if I go 0, right, let's do f of 0. If I plug in f of 0, again, I'm going to have 0.5 times 0, right, plus 3. That's going to give me 0. So what's the the greatest integer that is less than or equal to 0, it's going to be the same thing. So if I round 0 down, it's going to stay as 0, and this is where it would change, because now I would have 0 plus 3, and my output for these numbers would become 3, which means that if I plug in 0 for x, my output of f of x is going to be 3. So 0 is going to go all the way to 3. I'm going to have a closed circle at 3. So now our steps are basically 2 units long. And so once you see the pattern that is happening here, you can assume the pattern continues to happen. So at positive 2, or sorry, at 0, I'm going to have an open circle right here, because at negative 0.01, I'm still going to have an output of 2, but once I hit 0, now I'm going to have an output of 3. Well, this pattern continues to happen, and now we can follow this pattern along, where I'm going to basically span 2 x values and then jump up a y value that goes like this. And I can keep doing that over and over again. You can keep plugging in these values, but this should give you a 3, this should give you a 4, this should give you a 4. Okay, so this is a step function, and basically what happened there is because we had a 0.5x, that meant that, like 2x values or a span of 2 was giving us the same y value. And so we're going to talk about transformations in a little bit in 1.7, but this 0.5x actually represents a horizontal stretch. So imagine this function is being stretched out left and right because of that 0.5x. If I made this 2x inside of the function, my steps would be really scrunched in, or 3x there, they'd be really scrunched in. It'd be like a compression horizontally. So anyways, that's how you do that problem. Just to make sure we have it, I will do one from the homework. So if you look at the homework, like number 7, 9, those are all greatest integer functions. So let's just do one of those, or one of these down here. All right, why don't we try number 9? Try that again. There it is. So we did number 9 right here. So if this is our function, again, let's say we're going to do it from scratch. We're basically going to just make a table of values, x and f of x. And we're going to plug in x values. I like to plug in x values that is going to make a whole number here, right? Which is pretty easy because any integer will make a whole number as a result of adding 1. Those are going to be our boundaries of our steps. Let me make some graph paper here. So let's say we have got an x and a y. And let's just plug in anything. Let's just plug in a 0, right? So then I would have the greatest integer that is less than or equal to 0 plus 1, or 1, right? This would round down to just 1. So I would have the point 0, 1 on my graph. So 0, 1 would be on my graph. I'd have a closed circle there. Now also, if I were to plug in anything above 0, I'm going to get the same output, right? So you don't have to do this for each one because you're going to sort of understand, how this works. But for example, if I plug in a half, right, that would be like saying, let's round down from 0.5 plus 1, so 1.5. Again, that's going to give me 1, right? And in fact, in this case, we should have it where any value from 0 all the way to 1 is always going to give us 1, right? So yeah, 0.5 will give us 1, but okay, so 0.5 gives us 1. But if I plug in 1, then it changes, right? So if I actually plug in 1, right, then I'm going to jump up a step, because now I'm going to take the greatest integer less than or equal to 1 plus 1, which is 2, which in this case is, of course, 2. So this is where it's going to jump up, and I would have 1, comma 2 as my point. So 1, and then now 2 would be up here. And so my steps would start to just simply go like this. I'd have an open circle right there because that's the boundary. And then this would go all the way to 2. And you could keep plugging in values into your table, but once you know the pattern, it's going to keep doing the same thing, and it's going to go negative as well if you wanted to keep going. Now, I believe in these problems it also asks for the domain and range. Okay, so if I were to say the domain in this problem, which x values are we allowed or are we graphing here? This would be all real numbers. So this would be from negative infinity to positive infinity. The range, right, is going to be all integers. And the formal way to write that in set builder notation, by the way, is going to be the set of all, let's say in this case, f of x values, the set of all y values, but we're calling it f of x here, such that these outputs, f of x, is an element of, that little e, it's an element of the integers. So we'd have this like fancy looking z there. So if you see this in like an answer key or something like that, this means the exact same thing. In the same way where we had all real numbers, we said x values such that x is an element of the r, right? That fancy symbol for r. Same thing here. The integers are all the whole numbers, which can be negatives and it can be positives. And so that would be the range. All right, so I hope that clears things up a little bit for the greatest integer function. You should be able to complete these. Number 29 is a little different because you have an absolute value inside of the greatest integer function. So try to do that one, but whenever you plug in for an x value, that output is always going to be positive, even if you plug in a negative. So when you look at this, instead of having steps, normally we go like this. Normally we have steps that go like this, and go over and then go over. And then instead of going negative, because there's an absolute value, you're going to see the steps like go this way as well, right? So it's going to like kind of give you an absolute value type of shape. It's going to go the other way, but our outputs are never going to be negative. So this one looks a little tricky, but there's two functions in one at number 29. All right. All right, so that's it. 1.7. I won't be there tomorrow, so you guys will be doing 1.7. I'll come up with some videos and stuff for you to do for 1.7, and I will see you guys on Wednesday.